All right, I trust you did well on quiz 31. Students in here did very well, so very pleased with how they did. Of course, we don't know about Hayden. He hadn't taken it yet. Skipped my class. Anyway, let's go and review some things we looked at in our last lesson, something that we talked about but was not on this quiz, and that was making radicals smaller. Now remember, there are some radicals you don't have to make smaller. Like, for instance, the square root of 25. You don't make that smaller, class. The square root of 25 is just 5. You just take the root. But the square root of 20, that you cannot take. That is what we call, class, irrational. Good evening, class. What would we call the square root of 20? Irrational, because it doesn't work out evenly. And I said when you deal with an irrational radical, the objective, like a fraction, is to make it smaller. How did we say we would make it smaller? Well, I said we have to do what to the radicand? Factor it. But not just any old way, right? I mean, 20 could factor into 1 times 20, 2 times 10, 4 times 5. You can factor it a few different ways. I said the key, Aubrey, was to factor it so that one of the factors was rational, in the sense that you could take the rational root of one of the numbers. Well, technically, you could always take the square root of 1, so we really don't need to worry about 1, because that doesn't help. That would still leave me with a 20 in the radicand. But which of the other factors is rational? The 4. So I'm going to keep the 4 times 5, and then what we'll do is we'll take the square root, remember, of the factor that can be taken evenly. Right, the square root of 4 can just become a... And we can't take the square root of 5. That's okay, we'll leave it as the square root of 5. So our answer becomes 2 times the square root of 5. And we've made the radicand a smaller number by factoring so that we had a rational factor and going from there. So if we had the square root of 32. Danielle, there's a lot of ways I could factor a 32, but I need a way so that one of the factors is rational. How might I factor a 32? 16 times 2. Now, if you don't know your 16 times tables, you might not have thought of that, but that's actually the best way to do it. You would like, ideally, the biggest rational factor possible. It's going to make your life easier, as I think we saw yesterday. I know we did in here. I'm not sure. I can't remember 2 years ago. But I know we looked at it yesterday, an example where we could make our life easier by getting the biggest rational factor. Danielle, what would my final answer be then?
Well, 4 is the square root of 2.
Good. We'll take the square root of the 16 to get 4. We'll leave the square root of 2. Now, you might have been thinking, I didn't learn 16 times 2 when I was in elementary school, but I did learn 4 times 8. Well, that's a good start, right? We could take the square root of 4, class. 2 times the square root of 8. But like I showed yesterday, just like reducing a fraction, it's possible to reduce a fraction and still have more reducing you could still do. The same would be true oftentimes with radicals, particularly larger numbers. Not that 32 is that big, but larger numbers may put us in that position where we've reduced it. The radicand is smaller, but I could make it smaller still. Class, I could now factor the 8 into 4 times 2. Where now I can take the square root of the 4, class, to get 2. I've already got this other 2 that's being multiplied. And then finally, I've got the square root of 2, which square root of 2, yeah, it stays exactly like it is. So my final answer would be, class, 4 times the square root of 2. Danielle got there quicker by using 16 times 2. If you see it, it helps. Even if you don't see it, though, get what you can get. Start the process. Right? And so we'll look at some bigger radicals here in a moment. What about the cube root of 40? Well, again, we might be thinking, ooh, I know 40 can factor into 4 times 10. And if this were a... I don't know what just happened. Weirdness happened.
It just cracked.
It just glitched funny. It said disconnected and then it reconnected again. Anyway, I don't know what we lost. We'll find out. All right, we got the cube root of 40. If I just lost you there, this is how it works out. 2 ways to do it. All right, cube root of 40. 4 times 10, I said. Doesn't really help, because I can't take the cube root of either 4 or 10. But Evie, I could factor the 40 into 8 times 5, where I could take the cube root of the 8, class, 2, and I'll leave the cube root of the 5. The key then is to know what kind of numbers am I looking for. I'm looking for with square roots numbers like 4 and 16. I'm looking for with cube roots numbers like 8. So you might remember, if we go back in your mind to pre-algebra last year, I said one of the things I recommend doing is making a list of some key numbers that you might be able to use. Numbers that are perfect squares, numbers that would be rational factors. Numbers like 2 squared, class, 3 squared, 4 squared, 5 squared. Thank you, Danielle. The rest of you feel free to jump in. 6 squared, 7 squared, and so on and so forth, right? These are all those numbers. And by the way, we've got all the way up to 20 squared available to us for some of those bigger radicals. One of the main reasons I had you memorize those. Now, I will throw this thought out there. 16 times tables are hard. Okay, some numbers like 32, it's not too bad to see, but 16 times tables are hard. And after all, if a 16 works, a 4 would work, right? A 36 would work if 9 and 4 work as well. And 36 times tables, again, oftentimes hard to see. So if you're looking for numbers to try, 4. Because we have, let me go over here just a moment, we have a divisibility rule for 4.
These are for squares?
These are for square roots. For square roots, we have a rule for 4 if the last 2 digits are divisible by 4. So even a big number, hey, we can figure out if a 4 works. 9. We have a rule for 9. Remember, if the sum of the digits is divisible by 9? So we could use divisibility rules we've known for the past 4 or 5 years to help us with these. Now, we don't necessarily have divisibility rules for things like 25. But practically speaking, for a number to be divisible by 25, think money, it's got to end in 25, 50, $75, right? Like you learned counting by quarters. So if it ends in 25, 50, 75, or 00, you know there's a 25 in there. 49 is my none of the other ones are working one. If nothing else is working, it's probably a weird number. Maybe try 49, you never know. But again, you're looking at last 2 digits divisible by 4, the sum of the digits divisible by 9, 25, 50, 75, $1, or it's just weird. Okay, and so these are some of the numbers that we can try. And again, these are, if you're just not sure, if they're not on this list though, even the crossed out ones, if they're not one of these numbers or the crossed out, it's not going to help you, right? Taking a 20 and going 2 times 10. Well, 2 and 10 aren't special numbers. You can't use those for square roots. What about cube roots? Well, what would be my smallest perfect cube that does me any good, class? 8. 1 cube doesn't really help. So 1, okay, big deal. But 2 cubed or 8 would be a good one. We don't really have a good rule for 8, but it's not a hard number to divide by because it's single digit. What about the next number? 27. For here, you realize to be divisible by 27, it has to also be divisible by 9. So if I see that it's divisible by a 9, I might try the 27. The next number would be? If 64 works, 8 would work anyway, right? So I'm kind of in the same boat with the 64 as I am with the 16 and 36. 8's easier to divide by. I'd rather just use 8. And the next one, again, to be divisible by 125, you know 25 would have to work somehow, some way. So therefore, you're kind of looking for that 25, 50, 75, or 00 again. So these are the numbers we're looking for. Bigger numbers, okay, they might happen, but these are the key numbers that we need to use as we try to reduce our radicals. Look at page 281 in your textbooks now. Page 281 in your textbooks. And they've given you a bunch of radical expressions that they want you to simplify. Now, simplify could mean you take the root, if it works out evenly. Simplify could mean you reduce the radical. That's what it's going to mean most of the time. I want you to just do 1 through 13, the odd numbered problems. Page 281 in your textbooks, 1 through 13, the odd numbered problems. Just another minute or so to be finishing up. All right, pencils down, even if you're not finished with all of these. Number 1, what did you get for your answer, Danielle? 7. Don't try to reduce it, just take the root, it's rational. Number 3, what did you get for your answer, Aubrey?
3 times the square root of 8.
You're not wrong, but you're not finished. She did what I think a lot of us would do. She said, hey, I know this is 9 times 8. That's 3 times the square root of 8. But, Aubrey, we could then factor the 8, and that would allow us to get 3 times the square root of. So our final answer should have been 6 times the square root of 2. Now, there is a faster way. For those weirdos who recognize that 36 times 2 is 72, that's a great way to do it. And I say weirdos, but really, this is actually one of my go-to methods when I get a bigger radicand. If it's a big number like this, I think, well, let me try cutting it in half. Maybe the other number is a perfect square. Or, if half doesn't work, let me try dividing it by a 3. Maybe cutting it in thirds. Maybe that would work. If that doesn't work, I never try fourths, because 4 is already a perfect square, right? But I might try fifths. So you can try dividing by a 2, a 3, or a 5 if it's a bigger number, and see if maybe it gives you a perfect square. But 6 squared root of 2 should have been our final answer on that one. Number 5, what did you get? There's a bigger number. Evie? Yeah, it's a big number, right? And I don't like big numbers, so I look at it and say, well, instead of being like, well, look at the last 2 digits. I know there's a 4. We could be here all day. With a bigger number, I'm going to say, well, let me try cutting it in half. What is half of 128, class?
64.
Is that a square? Hey, it worked. It doesn't always work, okay? But with bigger numbers, that's my go-to first. See if cutting it in half works, and we get the 8 square root of 2. Ladies, did you also get 8 times the square root of 2? All right, what did you have?
4 times square root of 8.
Okay, and again, not wrong, just not quite finished, right? One more reducing would have happened. I mean, again, you could have said this is 4 times 32 to get 2 squared root of 32, and that's 4 times 8, so that's 2 times the square root of 8. Okay, that's 4 squared root of 8. And then divide by 4 again. Like, it could have worked that way, but much more efficient to try cutting it in half. Does that make sense on the big radicands? Try to find a shortcut, a lazy man's shortcut. Number 7, the cube root of 81. So I'm not thinking squares, I'm thinking cubes here, Danielle.
30 times the square root of 3.
Times the cube root of 3.
Yeah.
Good, that cube root of 81, we had to factor it, how, Danielle?
Into 3 times 27.
3 times 27, where I can take the cube root of 27 to get a 3, and then we'll leave the cube root of the other 3. Great job. Number 9, Aubrey.
9 times the square root of 3.
Good, 9 times the square root of 3. Here's another example where, as I said, it's a big radicand, right? Try cutting it in half. It's not an even number. Don't waste your time cutting it in half. What's your next try? Cut it in thirds. Try dividing it by 3, and 3 times 81, boom, there's my answer, 9 times the square root of 3. Is that what you did by any chance? That is what you did, excellent. You could have also said, well, the sum of the digits is 9, so I know it could factor into 9 times. Now hold on. 2, and there's a 6, a 7, and that's 3 times the square root of 20. Hey, that could factor again into 9 times. That's another 3. Hey, and there's my 9 times the square root of 3. You could do that. Nothing wrong with it. I'm just lazy. And so I try to take the shortcut with big radicands, cut it in half, divide it by 3. If that doesn't work, maybe try dividing it by 5. Questions? All right, looking at number 11, another big one. Square root of 450, Evie.
5 root of 14.
I think we might have had a multiplication error here. You've split 450 into 25 times 14? Yeah, it's 25 times 18. Yeah, so just a little multiplication error there. Danielle, what did you get for number 11? Square root of 450?
Because I started working that one, but I just did the 5.
The 25?
I tried to divide 5.
You tried to divide it 5.
And
All right, 5 and 90, is that going to work for us? No. I would start again. Try dividing it in half. Just cut it in half. 2 times...
225.
Hey, wait a second. We know 225, class. 15 times the square root of 2. There's our answer. Again, it would work with the 25. You do 25 times 18 to get 5 square root of 18. And then that would have factored again.
Into 9 and 2.
9 times 2. And there's the 3 times the square root of 2 times the 5. So there's the 15 square root of 2 the other way. Right? Questions on that one? Starting to feel a little bit better about how to handle the big ones. Don't let them become big problems. Outsmart them. Be lazy. Looking at number 13, back to Evie for redemption. The square root of 125?
5 times the square root of 5.
Good. Factor into 25 times 5 to get 5 times the square root of 5. And the number, that's where we stopped, right? We stopped with number 13. In your notes, let's go and do a couple more of these. I want to do another one of the big radicals. Let's do another one of the big ones here. The square root of 288. The square root of 288. What do you think here, Danielle? Cut it in half? All right, what is half of 288? Does that work for us?
12 times the square root of 2.
Boom, no trouble at all. What if it hadn't worked cutting it in half? For instance, what if we had something like the square root of 150? What's half of 150, class?
75.
75. Is that a square? Okay, then try cutting it in thirds. 3 times 50. Is that a square? Almost. 49 would be a square, but 50 is not quite a square. Would I try dividing it by 4, class? No. We could try dividing by 5, but that would be 5 times... Just have to see the back. It'd be 5 times 30. That doesn't work. Well, you know what, though? It's 150. What square do we definitely know goes in? We definitely know 25 goes in. So if the first couple tries aren't working, you know what? We know it's 25 times, let's see, how many quarters in a buck 50?
6.
6 quarters, right? So we know our answer would be then?
5 times the square root of 6.
5 times the square root of 6. Make sense? What if, instead of just giving you the square root of 150, what if I said 4 times the square root of 150? Well, that means it's 4 times the square root of 25 times 6, which means it's 4 times 5 times the square root of 6, which means my answer would be, class. So if there is a coefficient in front of the radical, doesn't change anything, just keep it along the way, and when you finish reducing, multiply the reduced rational factor by the coefficient up front. So write this one down. 5 times the cube root of 72. 5 times the cube root of 72. Now, with square roots, I like to try cutting it in half and thirds and things like that. Cube roots, there aren't that many cubes. So I usually just try the cubes. What cube do we know has got to work in 72, Aubrey? 8. We know the 8 has got to work. This is going to factor to 8 times 9. Now be careful. Students will look at the 9 like, oh, I can take the square root of 9. It's a cube root. Leave the 9 alone. Focus on the 8, class. Cube root of 8 is 2. And I'll just put it out here. That's a 2 times the 5 that was already here, class. 10 times the cube root of the 9. Again, the 5 did not affect the reducing step at all. It just gave us something to multiply the rational factor by. Does that make sense? Write this one down. 3 times the square root of 28. Walk me through. What should we do on a problem like this, Evie?
You do 4.
Times. Brain shut down. 4 times 7, there we go. Brain started working again. 28 is 4 times 7. Good. Remembering our multiplication tables. Thank your elementary teachers for that. And we'll take the square root of the 4 and make that a 2, which gets multiplied by the
3
to get 6, but we'll leave the square root of the 7. Do we see what we're doing here if there's a coefficient in front? What if I saw something like this? 108 to the 1/2 power. Fractional exponent? Well, class, a fractional exponent indicates a root. A fractional exponent indicates a root. Specifically, 1/2 power, class, means what?
108, or the square root of 108.
The square root. If you want to, write this in your notes. In fact, write it in your notes even if you don't want to. 1/2 power equals square root. The 1/2 power is just another way of saying square root. So when we see 108 to the 1/2 power, I'm going to rewrite that as the square root of 108. Stay with me. We're just going to write this as the square root of 108. And then we do exactly what we did. That's kind of a big number, isn't it? Well, let's try cutting it in half. What is 2, or 108 would be 2 times, is that a square? No, okay. Well, cutting it in half doesn't work. Try dividing by 3. Let's see, 3 times 36. Does that help? Hey, there we go. What's my answer going to be, class? 6 times the square root of 3. Easy enough. Write this down. 3 times 128 to the 1/3. 3 times 128 to the 1/3. 1/3? What do you suppose the 1/3 power means, class?
Cube root.
Cube root. Write that in your notes. The 1/3 power means cube root. So this becomes, now careful, what is raised to the 1/3 power, class? Just the 128. So this becomes 3 times the cube root of 128. Do we see how that's written? Now, cube root. I don't have a whole lot of cubes. What's a cube we might try? We don't have a whole lot of cubes. 8's one of them. Let's see if 8 works. 8 times, let's see, 8 goes into 12? Once with 4 left, 8 goes into 48? Oh, okay, so we can take the cube root of the 8, class. 2 times the 3 times the cube root of, but I can't leave it that way. Careful, not 4. Square root of 16 is 4. Cube root of 16, though, still factors. 2 times 8, right? 16 would factor again with another 8 times 2. Pull out another 2, because the cube root of 8 is 2. Remember, don't pull the 8 out, pull the 2 out. And we end up with, class, 12 times the cube root of 2. Now, this is one instance where you say, well, I could have cut it in half. Yeah, it's actually true. 2 times 64, the cube root of 64 would have been the 4 from the get-go, so it could have worked there. Doesn't work as often with the odd roots. Page 281, I want you to do numbers 15, 17, and 19. Take just a couple minutes, do 15, 17, and 19. They're on page 281. (15, 17, and 19). sake of time, we need to go and wrap it up here. Let's take a look. Hopefully you realize I don't need to reduce the square root of 81. It's rational. Just take the root. It's 9. 7 times 9 is just plain old rational 63. How many got that on 15? How many tried to reduce the 81? You're like, well, I could factor that into...
I have the 9. I just didn't like put it with the 7 and...
okay, does that make sense though? Just like when we take... Now here, I'm like, wait, we literally just saw a cube root of 128, right? Okay, I remember 64 times 2, so I'm going to go with the cube root. Careful, not the square root. The cube root of 64, class. 4. That gets multiplied by the other 4, just like the 9 got multiplied by the 7. That gives us a 16 times the cube root of the 2. And we saw the 32 toward the beginning of the hour, or the beginning of this part of the video at least, where we factored the 32 thanks to Danielle into 16 times 2. So there's my 4 times the 2, 8 times the square root of 2. Questions on this? All right, homework for this evening is to do the evens 2 through 20 on page 281. 2 through 20, the evens on page 281. Page 281, 2 through 20, the even, and you are dismissed.